So after I created the 2 videos about how to use the video analysis tool called the tracker, I created an assignment for my students to simply apply the software and the skills that they learned from the previous 2 videos, and the task would simply be investigating the acceleration due to gravity, because that will probably be the easiest thing that you can do. So I asked them to practice and also film a video by choosing an object. One is the heavy object, which could probably be a coin and is not subjected by the air resistance as much, while for lighter object that could be maybe a piece of paper that you can maybe slightly squash it to make it fall with significant air resistance. And so in the study, you may want to compare the acceleration of each other, and so explain why that would make a difference. So if you like to do that, you may want to pause the video. If not, we're going to review that right now.
And so I'd like to ask his co-star David Forbert to accept the award on his behalf. David. David, perhaps you'd like to say a few words, David.
Issue number 1. In this graph, you can see that the line was drawn from point to point, which is not something we want in physics. In physics, we always, really always, we want to draw a line that can represent the overall trend, and it will usually be a straight line or a smooth curve. So it doesn't really matter. I'm not talking about you should draw a straight line or a curve. It's really about you should show the average trend, and the line will eventually be represented by a mathematical model. So for example, for straight line, it will be y equal to mx plus c. For quadratic equation, you should know that is a times x squared plus bx plus c, something like that. So for a line that is from point to point like this, you would never get a mathematical equation to express that, and that actually means it will be meaningless to draw such a line. Issue number 2. Here is a VT graph of a heavier object, and you can see that when this student tried to find acceleration, he used the traditional method which you learn in maths, rise over run, or you call it delta y over delta x. Because obviously you can see that he picked up the coordinate of 2 points, probably from his data, and you try to calculate that acceleration. In fact, what you can do is you can simply read from the software right here the value of the equation. So the equation is at plus b, and so therefore the a is actually representing the slope of the line that you are drawing here. This is something that you should do instead by taking the advantage of using the technology. And of course, I think there's also another issue that I just accidentally find here, which is the unit is wrong. So you can see that according to this, it is -9. If I zoom in more, it is -9.25 times 10 to the power of 2. So like what he calculated is around 900 something meter per second square. And obviously this is not right, because we know the gravity on Earth is about 9.1 meter per second square. So I believe it's because of the units that he input, he mistook the cm to meter. Issue number 3. Here is the VT graph of the lighter object done by another student. You can see that the line of best fit, which is a straight line he draw, is like this. The issue is that we actually should all know for the VT graph of a lighter object is actually changing. You can't actually find the constant acceleration out of that, because the air resistance will change by its velocity. So let me show you how we can do it properly. Here is a library video I took from the software again, and you can see these are paper cups, and actually both of them will be subjected by the air resistance anyway. I will take the yellow one because I think that one is more obvious, affected by the air resistance. So I'll click here, click analyze, and I'll be able to find the data here, which show a line of best fit like this. Okay, so again, this is not something good because this doesn't represent the whole motion at all. We actually know it will probably be the best to show a curve, but then we just want to find the slope because we just want to know the acceleration, right? So what you can do is you can actually highlight this 3 point only. So this purple line represents the slope of these 3 point only. If you want to express even better, you can try to hide the line, which I can click here, then you can hide the line. So you can then again you can find the acceleration is greater because at the beginning the air resistance is not as high. So then for this case the acceleration is around -4 meter per second square. If you try to see the later part, you can see the slope here is rather gentle. So in this case the acceleration in the later stage is -1.4 meter per second square. So once again you can hopefully see that the air resistance is actually changing, and so depending on when you want to find, actually if you try to find the last 2 points, it's basically 0. So at this point it reached the terminal velocity already. So this is some way that you can try to select the part that you want to analyze, and you should have the physics knowledge to understand why we have to only choose part of it. Issue number 4. This is the screen capture of the motion of another student dropping the textbook, and this is a graph that she did. So she concluded that from the slope, the acceleration due to gravity is 12.36 meter per second square. Okay, I'm not talking about the unit, but the value itself, 12.36. So the problem is when you find there's a value that is much bigger than the expected value, which is 9.81 from the literature, then there should be a reason for it. I mean, we shouldn't have a number that is much larger than that. So what do you think about the problem would be? You can pause the video to think about it.
Imagination.
Okay, here's what I think. It may not be perfectly true. This could be one of the possible reasons. As you can see in the calibration length here, which is simply 15 cm that she said, it is too short. Think about this. Whenever you do any measurement or any kind of calibration, there's still an offset or an error from the actual value. So when you say this is 15 cm, it may not be exactly 15 cm. So let's say if you have 1 cm of error in your measurement of 15 cm, so it will be 15 plus or minus 1 cm bracket here. In terms of percentage, that will be 1 over 15 equals to around 6.7% of error. And think about this. If we simply think of this, and that is the exact error you have for acceleration as well, then for a literature value 9.81, you may have 1 plus 6.7%, and that should give you 10.464 meter per second square. So of course this is bigger than what we expected, but it doesn't seem to be enough to explain why it was 12 point something in her calculation. And so if you could measure a length that is much longer, so for example it is 1 meter, so 100 cm, even if you also measure 1 cm off, it will simply be 1 over 100, which is 1% of error. And talking about the gravity, which is 9.81, having 1% of error would give you just a number of 9.9081, so doesn't seem a lot in this case. And therefore it is strongly recommended that you can take as long calibration length as possible, as long as it is reliable. So what's the issue then? Why would she get 12.36 meter per second square in that case? We already see that the line of best fit is pretty well judged, and we also find that maybe of the calibration length, but that it shouldn't be giving you such a large error. there should be another source of error in this case. Think about it. I'll give you 5 seconds. Here's my answer. My explanation is because of the object and the calibration length are not in the same plane, and therefore there's an error. As you could see from the picture here, she dropped the textbook for a certain distance away from the wall, while the calibration is on the wall itself, so that would produce an error. As you could see, if the same guy here, of course it will be the same height throughout. Standing closer to the camera will give a longer distance you can measure, which is 2.24, and while he walks away from the camera, he will appear to be shorter in that case. So either way, it would not be accurate. Only when he is next to the calibration length that is in the same 2D plane here, then it will be accurate. So this is something that you should always pay attention when you do the video analysis. If you have any other ideas of why it would be much bigger, you can put your comments below and we can discuss. And so for the rest of the video, let me show you a good piece of work from my student. So here we go. First of all, he used a relatively high speed camera. As you can see, the frame per second is 240. Normally, if you just use a common mobile phone for his camera, it will be around 60 frames per second. So in that case, the motion, it will be more like buried sometimes. When the object is moving too quickly, then you cannot locate the exact position. So if you could have using a better camera, for sure it will be more helpful for sure. So that's why within a short distance, like he didn't do a long distance, he also did like 1 meter only. He could actually take a lot of data point right here. So in that case, it would be making your data more reliable. The second thing that you may find here is, like we said, he chose part of the data. As you could see, this is a more relative, the constant slope you can find, while it's actually changing, to be honest. As you can see later on, it's around 0, which is the point where it starts to have the terminal velocity. So choosing a certain area, since you know the slope is changing throughout the whole motion anyway, it will be useful to do that. And it is certainly allowed as well, as long as you can explain using the physics concept. Right down below, I really appreciate how the representation is shown here, which you literally write the equations here, so I don't have to look into the photo to find it. Even though you still show in the picture as an evidence, it will be appreciated to show that in this format, because this is v equals to a number times t, right? So this is the equation that you actually look for, and the slope here will actually represent the acceleration. One thing about the y-intercept that you may think is very strange, that is 174, is that because that's the case, that means the y-intercept will be 174, but then I don't think in the motion you ever reach 174 meters per second. And the reason is, if you look back in his graph, the x-axis is time t, right? But then at the beginning of his data is around 17 something second until 18 something second. It just actually happened in 1-ish second, right? But then if you think about the whole graph, it will be something like this. You have the axis like this, and this is v, this is t, and just now we have start actually from 0, is a bit more like, actually not from 15, actually start from 17, so around here. That's actually too much already, like around here only. And so if you try to think about, that's a straight line that we draw, let's say, then you may be extending this until it reach y-axis. And in that case, then that will be maybe 170 something, right? That's the y-intercept that we find. But then the issue is, of course, this is a projection only, and that is not true, of course, right? Because our motion only starts from here. So one way that you can do is you could go and take the raw data, and as you can see on the right hand side, you got all the velocity and all the time. You can actually reset the time, or I think you can actually do it on the software as well. If not, you can actually copy this. You can actually on Excel file, you can somehow use some simple algorithm to reset the first frame that you take as 0, and the next frame is just a difference between these two data points. So in that case, you can kind of shift the whole data to the right time frame. And so in that case, you'll be able to get the same slope, but getting rid of the y-intercept, like a strange y-intercept like this. One good thing that he finds is using some research skills to find out that actually there's a drag equation which equals to half c, which is the drag coefficient, times a, which is surface area, times v squared, which is the velocity of the object. Actually, is relative airflow. But okay, I think that's actually fine here. Furthermore, you can actually find out there is an equation governs the terminal velocity and things related to this. In fact, without researching, you can actually prove it by yourself. I would like to let you try. Maybe you can pause the video if you want to. Pause the video, try it out yourself.
A few moments later.
Okay, let me show you how you can do it. So think about an object reaching terminal velocity, then you have the weight balancing with the air resistance, or you can call it drag if you want to. And in this case, then obviously you can write the equation that is mg, which is the weight, equals to drag, right? Because you reached terminal velocity already, and that means net force is 0. And earlier, according to the research, we have the drag formula, which is half times coefficient of drag, area, v squared. And in fact, the equation was actually, I think there's a mistake here. There should be a rho, the air density there. So in this case, you can simply rearrange the equation to the form that you like. So if you like to express v, which is terminal velocity, then obviously you can do so as well. So that will be mg divide, you can times 2 here, and then divide coefficient, divide a, divide density, and give it a root. So that should be the same equation that we find, which is right here, right? You can see it's exactly the same. So he also find out the literature value of the things that he used. I think he also measured the mass, try to find out the density of the air, and also measure the area, and also try to find the folder, it's just a normal A4 folders shape, what kind of drag coefficient it will be. This value is from experimental. So the best thing is he tried to substitute everything inside, and he tried to find out the theoretical value is actually 4 point something as well, which match with what we find out from the experiment. Here is the actual best part of his piece of work. So if you remember in the second video about video analysis, I used the software to find out the gravity of Mario World, and so he also tried to use the same idea applying on to another game called the Minecraft. I personally did not play that, but I'm fascinated on how he tried to find out the answer. Okay, so the way that he did was to try, of course, take a video of the character jumping, and so he made an assumption of having one block is 1 meter, which I think makes sense because I guess you can say well, this is exactly 1 block, I mean 2 blocks in total. For a person, I think that is quite fair already, right, as a more like an integer value. He somehow managed to use a certain software to record it at a certain pretty good frame per second, and this is his graph eventually, alright, also a VT graph as you can find. Like so, you would like to choose the part where it's relevant. Obviously, this is a part where I think the character is jumping instead of falling down. So this is a point where the character actually falling down, and he find out the value using the scale, and that is negative 30.3 meter per second squared, so which is around 3 times of the Earth. I actually tried to find on Google which I think there are some other people also use other method to find out the gravity, which quite coincide with what this student find. Even more, he tried to decompile the program, even though I don't know how you can do that. Is Minecraft an open source software or game? I don't know. So I guess in that case you can decompile the whole program, and he tried to read through all the lines of the programs, and he find out some formulas related to the gravity in itself. So he find that it is also quite similar, quite close to the one that he find out, and the exact value is 31.36 meter per second square, and I think this is a really good finding. He also tried to see whether or not there is a terminal velocity or any sort of drag function in the Minecraft physical engine, and he find out there isn't, and the reason is probably because they use hardcode, and the reason is because maybe they want to lower the performance requirement. So that is to say, you may not experience the realistic terminal velocity, say if you try to jump from a really high distance in Minecraft. That's all for this video. I hope this video can tell you more about what to pay attention to when you're doing a video analysis, and also its limitation. At the same time, hopefully the good example can show you the potential of what you can do with video analysis as well.